Today we're going to be talking about solving linear inequalities in one variable. We'll start with some basic concepts and see what differences we have between equations and inequalities and solving them. Then we'll do some examples of solving some linear inequalities by hand, graphing some solution sets. We'll look at a few compound inequalities as well, and look at some technology methods. So inequalities include the relations that include less than or equal to, greater than or equal to. And you can see the symbols for them there. And whereas solutions to equations typically consist of only one value or a few values, discrete points, solutions to inequalities typically consist of entire intervals of real numbers. The boundaries of the solution intervals are determined by solutions to the equation found by replacing the inequality by an equals. So in other words, replace the less than with an equals, solve that, and you found a boundary of your interval that's going to be a solution set. So the techniques for solving linear inequalities are pretty much the same as the techniques used for solving linear equations. There is one major difference, though, you have to be careful about. When you multiply or divide both sides of an equation by a negative number, we must reverse the direction of the inequality sign. When I say reverse the direction, I mean a less than becomes a greater than. A greater than or equal to becomes a less than or equal to, and so forth. Now you can add or subtract the same amount to both sides. Makes no difference whether you're adding or subtracting a positive or negative. The direction stays the same. You can multiply by a positive number on both sides of an equation. The direction stays the same. But if we divide or multiply by a negative number, we flip the inequality over. So just to show you why you need this, it's basically what happens when you multiply by a negative, and what this does to the order, how we order our numbers. So notice that 3 is less than 5, but if you multiply both sides by negative 3, you get negative 3 and negative 5, but negative 3 is greater than negative 5. Think about how these things line up on a number line. Now another way we could start with 3 is less than 5 and get to negative 3 is greater than 5 is by adding negative 8 to both sides. So if you add negative 8 to both sides, you get 3 plus negative 8 is negative 5, and negative 5, or positive 5 plus negative 8 is negative 3, and so we get negative 5 is less than 3, which is true. And another way to write that is to write negative 3 is greater than 5. So of course when you're switching sides, then you're switching the inequality as well. The wide part of the inequality points toward the larger number, and the pointed part, the vertex there, points toward the smaller number. Smaller meaning further to the left on the number line. So let's look at some examples here. Here are 3 examples. And notice that I'm using exactly the same techniques that we use for solving linear equations. So the first example, it says 3x minus 4 is less than 2x plus 3. So I want to get my x's on the left and my constants on the right. So to do that, I need to eliminate the x or variable term on the right side. I do that by adding negative 2x to the right side. That annihilates the 2x term. The 2x and the minus 2x add up to be 0, and so that basically wipes that out. But of course, I have to do the same thing to the other side, add negative 2x to the left. Then that's going to give me 3x minus 2x is 1x on the left, but then I still have this negative 4 on the left, so I want to get rid of it by adding positive 4, and then negative 4 plus 4 cancels out. But if I add positive 4 to the left side, I have to add positive 4 to the right side. 3 plus 4 is 7, and so we get x is less than 7. You can check this because this 7 should be the point that makes this an equals true. If I replace the less than with an equals, it would be true. So plug the 7 in. 3 times 7 is 21. And then 21 minus 4 is 17. That's what we get on the left side. On the right side, we get 2 times 7 is 14. 14 plus 3 is 17. 17 equals 17. That's true. So that is, we found the correct boundary point. So you can. That's how you want to check your inequality first of all. The first part of the check to see if the boundary point is right. To see that the direction is the right direction, check it. Check a number where x is less than 7. Good candidates to check 0, -1, +1. Those are easy numbers to do arithmetic with. So let's just check with 0. So if I plug in 0, 0 is less than 7, so 0 should make this a true statement. 3 times 0 is 0, minus 4 is -4 on the left. On the right, 2 times 0 is 0, plus 3 is 3. -4 is less than 3. Yep, that's a true statement. So 0 is in the solution set. So if you check those two things, you check to see that the boundary is correct, and you check to see that any one point in your region is correct, then you know you have the correct boundary and you have the correct direction on the inequality. Now, the way we state our solution set is some statement about x. We can state this as a set of numbers and say x is an element of that set of numbers. And we might do this in interval notation, or we might do it in set builder notation. In interval notation, x is less than 7 says we go from forever left up to 7, but don't include 7. So that's open parentheses, -infinity, comma 7, close parentheses. So that's an open interval, okay, from -infinity to 7. Okay, or that would be interval notation. And set builder notation, that's written as the set of all x such that x is less than 7. And then we can also graph that, and notice our graphs to our answers are on a number line. Graphs to our answers on equations are also on a number line, but they're typically just 1 point or maybe a few points. Here we have a whole interval here going from forever left up to 7, and notice we have an open circle at 7. Some people would actually put a right parentheses there, rounded parentheses, but I prefer to use an open dot there that's not colored in. And so that says that it goes up to, but not including 7. So it goes all the way up to 7. However close you want to get to 7, as long as you're on the left side, that's still included. So for example, it doesn't stop at 6 or 6.5 or even 6.9. It goes all the way up to, but not including 7. Let's do the next one down here in the lower left. -5x minus 4 is less than -7. So here I already have the x on the side, but it's not by itself. So remember, when you have both multiplication and addition, and of course we want to think of the subtraction really as plus a -4, so we have multiplication and addition. We want to get rid of the addition first. So this has plus a -4, you will change that by adding a +4. Of course you got to do that to both sides. And so we get -5x is less than, well, that's messed up. Let's see if we can fix that. Okay, we're going to fix that here real fast. So that should say -3, and this is when I did a copy and paste and didn't finish it, okay? And this should be -3 divided by, okay, let's watch what's happening here. If I take this same expression here, okay, and I want to divide both sides by -3, by -5, excuse me, that's what I want. Now that'll get me an x on the left. Okay, so that means I got to take the other side, which was -3, and divide it by -5. But at the point we do this division, we have to switch this to a greater than. Okay, and the -5's cancel, leaving x, and this cancels the negatives, and we get 3/5. So we get x is greater than 3/5 or from 3/5 to infinity. Okay, so that's what that should look like. And is my graph? My graph is probably off. By the way, 3/5 is also 0.6. So I could also write that as, for example, the interval from 0.6 to infinity. I could write it that way if I wanted. Okay, and then the number line's off a little bit. I've been using a thing in Geometry Sketchpad to graph these, so it won't hurt you to watch what I'm doing here. I'm going to go into my sketches, and I think this one's actually under arithmetic, under intervals. And I can graph, here's a number line, and this one I can graph some things I want a greater than, and I want to put in, I can type the fraction in, was it 3/5? Like that, and you can see the graph here. And I'm going to copy that and paste it into my PowerPoint. So there we go. Hopefully this is good. Okay, so let's continue our slideshow here. Okay, so now notice that this is at 3/5 or 0.6. That looks about right. From there on to the right forever. Notice we do not include the endpoint there again because this is an open interval, because the equal to is not included in the original. So that means it's a round marking there, the parentheses in the interval notation. Okay, let's look at this next one. 4x minus 3 is greater than or equal to 9x plus 5. So here I'm going to subtract 9x from both sides and add 3 to both sides. Notice that eliminates the x term on the right and the constant term on the left. So that gives me negative 5x on the left, greater than or equal to 8 on the right. Now at the point I divided by, I need to divide both sides by negative 5 to get the x by itself. When I do this, I reverse the inequality because I'm dividing by negative 5. Then I'm just simplifying the left and right side. The left side simplifies to just x. The right side simplifies to negative 8/5 or negative 1.6 in decimal form. So I could say that x is an element of the interval from negative infinity to negative 8/5, but this time I include the negative 8/5 because the or equal to part is included up here. And then, or I could write it as negative infinity to negative 1.6 because those are exactly the same. That's not a decimal approximation, that's just the exact decimal form for that particular fraction. Or in set builder notation, the set of all x such that x is less than or equal to negative 8/5, or I could write it as the set of all x such that x is less than or equal to negative 1.6. So all of those are good versions. When you're working one of these on the computer software, it may specify, I'll put it in decimal form, or it may specify, use the palette to make it in a fraction form. And then we might graph it as well, and you can see that the graph, here's our number line, and we're going from forever left up to and including negative 8/5, negative 1.6, and if you look, that's placed at the right place on the number line. Again, I use the software to do this, but you could graph these, at least get very close by hand, and you probably should label that point with its value. Alright, let's check these. We already checked the first one. Let's check the one we just did. If this checks right, we should be able to plug in negative 8/5. Here, let me just go ahead and just show you this by how I would do this, writing this out by hand here. So we have 4x minus 3 equals well, greater than or equal to 9x plus 5. So to check the boundary, we should get 4x minus 3 equals 9x plus 5 when x equals the boundary of negative 8/5. So 4 times negative 8/5 minus 3 should equal 9 times negative 8/5 plus 5. Or use decimals if you'd rather. So this is negative 32/5 minus 15/5, which is negative 47/5, okay? This is negative 72/5 plus 25/5. That is, I hope, negative 47. Let's see, 47. Yep, that works. So that checks. So that's part of a check. I'm not completely done. I have the right boundary point. How do I know I'm going the right direction? Well, let's check a point. You can check it either a point that works or one that doesn't work. So in this case, I'm gonna usually check the point 0 unless it is the boundary point. So if you look at this, 0 is not less than or equal to negative 8/5. So 0 should make this a false statement. So we're looking for a false statement here, greater than or equal to. So this is 0 minus 3, negative 3, greater than or equal to, this is 5. This is false, so that says x cannot be 0. 0 is not a solution. Well, look at our graph. 0 is not a solution on this graph, so the other side does work. I could be able to check any of these points on the other side. Let's see, what do we have here? We've got things like negative 2 would work. So I could check negative 2, and negative 2 does work. 4 times negative 2 minus 3 greater than or equal to 9 times negative 2 plus 5. Negative 8 minus 3 is negative 11. Negative 18 plus 5 is negative 13. And negative 11 should be greater than or equal to 13. It is. So that's true. And again, that one's supposed to be true, so that checks it out. Okay, let's check out this other one here. So I think we can just do it in our head here. So check out positive 3/5 should be the boundary. Plug that in. Negative 5 times positive 3/5 is negative 3. Minus 4 is negative 7. Negative 7 equals negative 7, so we have the right boundary point. 0 is not in this interval, so 0 should make this false. Plug in 0, this term goes away. Negative 4 less than negative 7. That's false. It's supposed to be false for 0, so that checks. Put in something bigger than 3/5 like 1, and it should check. It should be true. So negative 5 times 1 is negative 5, minus 4 is negative 9. Negative 9 less than negative 7, that is true. It's supposed to be true for negative 1, so that's good news. Now let me show you a way we can use some two-dimensional graphing to help us with this. So here we have, look at this one at the top here. If we want to graph 3x plus 6 equals 0, we've looked at this before. We're talking about we could graph y equals 3x plus 6 and see where it's on the x-axis, where y is 0. Okay? And of course we know that that's just when x is negative 2. Subtract 6, divide by 3, and we get x is negative 2. Or if you write it as just a set, x is an element of the set, just the set containing negative 2. And so the answer is this one dot right there where it crosses the x-axis. So if we were to graph the solution set on a number line, here's our number line below, the number line is just the x-axis. Sort of forget everything else that's up there and just graph the solution, which is the dot on the x-axis, because it's a single number, not really an ordered pair for a solution. X is just a single number, negative 2. There it is on on that. So really all I'm doing is bringing this x-axis down here. Now, from the same graph, we can tell some related inequalities. If we say 3x plus 6 is greater than 0, again, that boundary point is when x equals negative 2. But what we're saying is, if y is 3x plus 6, which is what we have graphed in blue here, same as before, then we're saying when y is greater than 3x plus 6, we're saying when y is above, we're saying when 3x plus 6 is above the x-axis. And so notice the graph here is above the x-axis. Which x's make that true? Well, all the x's that I have shaded in red on the x-axis are in orange down here. And so that is going to be our solution set, negative 2 to infinity. Notice we did not include the intersection point, but it goes to the right forever. Okay. Similarly, if we want the places where 3x plus 6 is less than 0, y is 3x plus 6, we're looking at when y is less than 0. Y on the blue graph. Well, where are the y's less than 0? Down here in the third and fourth quadrants when the graph is below the x-axis. So what part of this graph is below the x-axis? Well, this part over here, right down in here. And what axis is that? Well, that's from negative infinity up to this x-intercept at where x is negative 2. So we can graph that. Here's another example. If we want to take 2x plus 8 is greater than or equal to negative 2x plus 4, one way we could do this is to graph y1, or f of x, equals 2x plus 8, and y2, or g of x, equals negative 2x plus 4. We get these two lines. And of course, they're equal to each other when they cross each other. And so we need to find out that intersection point, which we can solve algebraically here. Add 2x to both sides, you get the x's are gone on the right, and you get 4x on the left. Add negative 8 to both sides, you get the 8 cancels on the left, and you get 4 plus negative 8 is negative 4 on the right. Divide both sides by 4, you get x equals negative 1. And that's the boundary point, and that's the point where they cross each other, at least the x value of that. If you plug it in, 2 times negative 1 is negative 2 plus 8 is 6. And so also on the right side when you plug in negative 1, negative 2 times negative 1 is positive 2 plus 4 is also 6. So they cross each other at this, or intersect each other at this point, negative 1, comma 6. Negative 1, 6. Well, we're interested in the x value of that. So if we pull that straight down, the boundary point there has an x value of negative 1. And that one is included because the or equal to in the inequality. Now what we want is an interval, and that's going to be our boundary point. Well, do we shade to the right or we shade to the left? Well, we want to shade where the blue graph, the f, is greater than the y values on the blue graph are greater than the y values on the purple graph. So where f is greater than g, or y1 is greater than y2. So where the blue graph, where is it above the purple graph? Well, that's to the right of this point of intersection. Anywhere to the right of this point of intersection, the blue graph is going to be above the purple one. And so we see that the solution set is from this negative 1 to the right forever. That's bracket negative 1 comma infinity parentheses if you do interval notation. Of course, in set builder notation you'd say the set of all x such that x is greater than or equal to negative 1. So if you think about this, this gives us a couple of different ways to look at how we can visualize our solution set to an inequality in one variable. When we have one variable, we're really just talking about graphs on a number line. If it's an equal to here for a linear equation, you just get the 1 point on the number line. If it's a greater than, you get an open dot at that 1 point shaded to the right. A less than would be that open dot shaded to the left. If it's a greater than or equal to, you would of course take this graph to the right and fill in that dot. But this visualization here shows how we can introduce a second variable, a y here, as well as our given x, and we can use a two-dimensional graph to visualize this as well. And of course, we're going to see how we can use some calculator methods for solving some of this. Or, well, you know how to use some calculator methods for this. You know how to do a calculate 0 on your calculator to find this point of intersection with the x-axis. And of course, that finds the boundary point. Then you just got to look at the graph of y equals 3x plus 6. And if you want the y here to be greater than 0, then you graph. So here y is greater than 0. So it's when 3x plus 6, that graph is above the x-axis. If you want 3x plus 6 less than 0, you're wanting y to be less than 0, so you're below the x-axis on the blue here. And of course we graph our final answer on just a number line, which is essentially just the x-axis there. Similarly here, if you've got a more complicated expression on both sides, you sort of have two options. You can solve 0 on one side and do it just like the previous one, or we can graph both the left side is, say, y1 and the right side is y2, or I call them f of x and g of x here, and we're just comparing where these things either cross. If we're doing the equal to, we just find the point of intersection, and that one point is the only answer. If we're doing a greater than, then we look at for where the left side is higher than the right side, in this case where the blue graph is above the purple graph. If we did a less than, we'd be looking at where the blue graph is below the purple graph. So that would be from negative infinity up to negative 1, not including negative 1. If it's a greater than or equal to, of course you include the boundary point, and the boundary point occurs at the x value where the two graphs intersect. Now let's look at some what we call compound inequalities. Compound inequalities are multiple inequalities connected by logical operators and, or perhaps or. Now remember, we've talked about this before. Or corresponds to which set operation? Union. And corresponds to which set operation? Intersection. So if we have 3x plus 1 is greater than 5, or 4 minus 5x is greater than 7, we can solve these independently first. So 3x is greater than 4, because we added negative 1 to both sides of that inequality. And we divide both sides by 3, we get x is greater than 4/3, or instead of 4/3 you can write 1.3 with the 3 repeating, which is the decimal version of 4/3. On the right side, 4 minus 5x is greater than 7. Subtract 4 from both sides to get negative 5x is greater than 3. Then divide both sides by negative 5 to get x is less than negative 3/5. Remember, we switched from a greater than to less than because we were dividing by a negative there. Negative 3/5 is negative 0.6 if you look in decimal form. So I just happened to write the set builder notation in fraction form and the interval notation one in decimal form, but you could have done either one in decimals or fractions. So I say x is an element of the set of all x, such that x is less than negative 3/5 or x is greater than 4/3. Well, let's look at that a minute. X is less than negative 3/5 is what I have as the brown graph, the second graph here. So it goes from negative infinity up to negative 3/5, not including negative 3/5. X is greater than 4/3 starts with an open dot at 4/3. That's the orange graph, the first one. And it starts at 4/3 and goes to the right forever. Okay? And that's the orange graph. Okay? Now, since I have the logical operator or, I'm wanting the union of these two, so anything shaded gets shaded in the final answer. So the final answer is the red graph at the bottom. And notice it actually consists of two separate intervals, and I can't list that as one interval in interval notation. I can list each interval separately and combine them with the set operation union. Remember, intervals are sets, so we combine them with set operations, unions, intersections, so forth. So, our final answer in interval notation, x is an element of the sets that we give here. So x is an element of the interval from negative infinity to negative 0.6, open interval. union, the open interval, from 1.3 repeated to infinity. And so anything that's shaded in red works. Now let's check this again, and you check it by checking your boundary points. And then we should check, maybe we'll check a point in each of the three regions that we have here, the two regions that are shaded and the one in between that's not shaded. So the boundary point should make one of the two equations equal to equals on both sides. So let's see, if we take the boundary point, and again our graph should probably label those boundary points. I didn't do that here, I probably should have. But if we label those boundary points, let's see, we've got negative 3/5 is the one boundary point. Now that's the one that makes the one on the right equals. So let's put that in. Negative 3/5 times negative 5 is positive 3, plus 4 is 7. 7 equals 7, so that's the correct boundary point. Check the boundary point on the right interval. That's the point 4/3. That's the one that's going to make the one on the left be an equals. 4/3 times 3 is 4, plus 1 is 5. 5 equals 5, so that is the correct boundary point. However, notice that 5 is not greater than 5, so that boundary point is not included. Similarly, the boundary point at x equals negative 3/5 is not included either. Now, if we check 0, that's the region, it's in that region between the boundary points, we should get a false statement. And for an OR statement to be true, they both have to be false. So if we put in 0 there on the left, we get 3 times 0 plus 1 is 1. 1 greater than 5, false, as expected. We also have to get false on the other one. 0 times negative 5 is 0, plus 4 is 4. 4 greater than 7, also false. So that means since 0 didn't work in either one of them, then 0 is not in the solution set, and that checks out with what we have graphed. Let's check something in the interval on the right. 2. If we plug in 2 on the equation on the right, let's see what happens. 2 times negative 5 is negative 10, plus 4 is negative 6. Negative 6 greater than 7? No, that's false. That's a false statement. Okay, that's okay because it doesn't have to make both statements true. It just is to make one or the other true. So if it makes the other one true, we're still okay. So let's try it in the equation on the left. 3 times 2 is 6, plus 1 is 7. 7 is greater than 5. Yes, that's a true statement. So 2 is included because it makes the equation on the left true, or inequality on the left true. Similarly, we could test out, say, pick an easy point. How about negative 1? Negative 1 is going to make the equation on the left false, but the equation on the right, I said equation, I should have said inequality. The inequality on the left false, and the inequality on the right true. So let's check it out. 3 times negative 1 is negative 3, plus 1 is negative 2. Negative 2 greater than 5, false. Okay, that doesn't matter as long as it makes the one on the right true. Okay, negative 1 times negative 5 is positive 5, plus 4 is 9. 9 is greater than 7, true. So that means that negative 1 is in the solution set. And so we see that our solution set, since it is two intervals that don't connect to each other, in interval notation you have to write that as two separate intervals, but any x's that are included in either interval are in the solution set, so we want the union of those two. And of course OR basically corresponds to union. And corresponds to intersection. So we're going to have an intersection of two intervals here. Okay? So again, we solve these separately. So we have 2x minus 1 is less than 7, and negative 3x minus 1 is less than 11. So here we add 1 to both sides on the left, and we get 2x is less than 8. Divide both sides by 2, we get x is less than 4. On the right, we have negative 3x minus 1 is less than 11. Add 1 to both sides, and you get negative 3x is less than 12. Divide both sides by negative 3, we get x is greater than negative 4. Again, we divide by negative, we reverse the inequality. So here we have x is less than 4, and x is greater than negative 4. So x is less than 4 is the brown graph, from negative infinity up to 4, not including 4. And x is greater than negative 4 is the orange graph, starting at negative 4 and going to the right. But the and says we want the intersection of those two. We want the overlap. And so the overlap of the two, the things that are still shaded in both graphs, is the numbers between -4 and 4. Another way to write this inequality, compound inequality, is to put everything in increasing order and write it in one inequality. It's sort of a 2-in-1. You write x is an element of the set of all x such that -4 is less than x, which is less than 4. So that's just a shorthand notation for saying -4 is less than x and x is less than 4. Of course, -4 less than x is the same thing as saying x is greater than -4. And so this gives you the numbers between -4 and 4. In interval notation, this is really easy to write in interval notation, and this is a really nice way to write it. X is an element of the interval from -4 to 4. Parentheses on both ends, so we do not include either the -4 or the 4. Another way to think of this is, instead of by shading, think of erasing. Think of it, if you say, well, if I don't have any conditions on anything and I want to look at a set of real numbers, then I have the entire number line shaded. But when I put the condition 2x minus 1 is less than 7, that boils down to the same condition as x is less than 4. What I've done is I've erased 4 and erased the things that are bigger than 4. So now we're down to the brown graph. But then we also have, and we have another condition. The other condition is -3x minus 1 is less than 7, which is equivalent to the condition x is greater than -4. So now what we've done is we erase -4 and the stuff that's less than -4. So from the brown graph, erase that part, and what you're left with is the red graph. So you can think of it that way as well when you have ands. So in ands, where we start with everything, we have one condition eliminate some stuff, another condition eliminate some stuff, and if we had a third one, it eliminates some more stuff perhaps. Ors are sort of, they're unions, so they build up. So if you have a compound inequality like this, 4 is less than 3x minus 2 is less than or equal to 13. Remember, this is like an and, but you can solve these without separating it back out. And so what we can do is add 2 to all three sides of this, because there are three parts to this, and that will get us to 3x in the middle, and add 2 to the other parts as well, so that gives us 6 on the left. Okay, so let's see, we've added 2 to all three sides. Now we've got the 3x in the middle. So now what we want to do is get the x by itself in the middle, and that is to divide by 3. We'll turn the 3x into an x. Then we have to divide all three sides by 3. 6 divided by 3 is 2. 15 divided by 3 is 5. And so we get 2 is less than x, which is less than or equal to 5. So if we write it in set builder notation, we say x is an element of the set of all x, such that 2 is less than x, which is less than or equal to 5. Or, in interval notation, it's probably the best way, it's easy. X is an element of the interval, parentheses 2, 5 bracket. So the 2 is not included, the 5 is. So when we graph it, we have an open dot at 2, a closed dot at 5, and we have solid everything between 2 and 5. Okay? So if we check this, plugging in 2 is going to give us the equal to on one side, and the 5 is going to give us the equal to on the other side. 3 times 2 is 6, minus 2 is 4. 4 equals 4, so that checks on that left side in point. And then 5, plug that in. 3 times 5 is 15, minus 2 is 13. 13 equals 13, that checks on the right. Notice that 13 equals 13 does work, so that is a solid dot, whereas the 4 less than 4 does not work, so it's an open dot there. Then we just check something. We can check things in each of the three intervals if you want. So we could check some number, looks like maybe 3 or 4 might be a good one to check. Let's try 3. 3 times 3 is 9, minus 2 is 7. 4 is less than 7 is true, and 7 is less than or equal to 13, so that's true. So that one's shaded. If it's shaded, all the ones between 2 and 5 will be shaded. And you could just check the other intervals if you want. Say anything to the left of 2 should not work, and anything to the right of 5 should not work either. So we could check, for example, 0. 3 times 0 is 0 minus 2 is negative 2. Negative 2 is less than or equal to 13, but negative 2 is not greater than 4, so it doesn't satisfy the entire thing, so it doesn't work. And it's not supposed to, because it's not in our solution set. And if we take another number, let's say something like, say 10, out here to the right, this should also not work. 3 times 10 is 30, minus 2 is 28. 28 is greater than 4, but 28 is not less than or equal to 13, so it does not satisfy that part of the compound inequality, so it is false, and it's supposed to be false. So, after studying this lecture, you should be able to solve some linear inequalities without using any technology. Just do it by hand. You should be able to present your solution set of your inequality in both set builder notation and interval notation, and as a graph on a number line. You can also use two-dimensional graphing to solve inequalities and to help you do that. You should be able to solve compound inequalities, and even though I didn't illustrate it here, you should be able to use calculators and computer technology to find and illustrate a solution to inequalities using graphical approach by the intersection of graphs method, which we did see, and the calculating zero. So you should be able to use the techniques that you learned in the last unit to find those points of intersections of graphs, or the points where the graphs cross the x-axis, and then use the concepts that we did here today to use that to help you solve some linear inequalities, or even some nonlinear inequalities, as we will apply this later on.